Right, in this video, I'm going to finish up 11.3. We did this in class, but we just didn't finish because we had a quiz on the same day. So there are a good amount of videos. I apologize. It's the only way we can make it through curriculum without me doing you a disservice. Um, missing out on sections that you actually may need in your following classes. So we're going to deal with applications. You guys have already seen applications of vectors, talking about force. We actually had one on the quiz talking about force. It was a statics question from physics. What we're going to look at here is we want to look at like the opposite, the reverse problem of that. We want to take a vector that already has a force, right? Something, a resulting vector, and we want to break it into what they call vector components. What this means, vector components, is that we're breaking it down to its horizontal, its x, right, and its vertical y. This is essentially trig. It won't take any calc. The following physical example enables you to see the usefulness of this procedure. So I want to show you this. We have a boat here. It's on a ramp. Okay, there is a force F due to gravity. It pulls it down the ramp and against the ramp. So it goes straight down on this like tilted ramp. We have two different forces. I have this like W1 force. That is the force of the boat being pushed down the ramp. And then the rest, the resulting fork goes directly into the ramp. So this is actually a right angle, and they show us that to the left there. But this is the boat shoving directly onto the surface. So with two forces, we will always have two, one pushing against. That will be, I'm about to give that a name. And then W2 is our orthogonal vector. It's orthogonal to W1. W1 actually has a special name. It's called the projection. So I'm going to define it, and then I'm going to show you a little more what this means. The usefulness for this W1 and W2 is that I have this. If I want F, I take my components of F and add them together. So this will help us analyze the effect of gravity on the boat when we get there. That'll be more for your physics class. W1 indicates the force necessary to keep the boat from rolling down the ramp. If I could take another force and put it against W1, we're going to actually do this problem in a little bit. It'll keep the boat from rolling down. Whereas W2 indicates the force that the tires must withstand. So W2 is a force going down from the tire. Okay, so I'm just going to leave it there. We're going to come back to this problem here in our next video, an application video. What we call this W1 here. Let me go ahead and draw a picture here. Let's call this F. I'm going to draw the components here to kind of give us more of a scope of what each one of these should look like. All right, we have two different vectors in blue here, and they are the components of F. Notice that the W1 is how much do we go far in the X, and then W2, that vector is how much we go in our Y. The W2 is the orthogonal vector to the component. W1 is what we call a projection. What is happening is if there was a sun, like a yellow sun, right above a star, and its sun rays are coming straight down on top of this, W1, the blue line on the bottom there, is called the projection of F onto whatever we want to call. Let's say that the ground here, let's say the ground is U, the vector U. We would say this is the projection of F onto U, which is W1. So W1 is the projection of F vector onto U vector. That's how we note it. And it's just like a shade, or shadow, I mean. It's a shadow of the F vector if the sun was directly above said vector, giving us the blue vector. All right, definitions and properties of these things. So let U and B non-zero vectors. So we know that U is equal to W1 plus W2, where W1 is parallel to V, and W2 is orthogonal to V. So that would be if I had V, right? So W1 is parallel to V. It's parallel to V, and then W2 is orthogonal. So if I had V, I keep using my eraser. This, right, is W2. And then we get this like weird shading here. That's W1. That's the projection. It says where W1 is parallel to V. Oh, I see what it's saying. Okay, on to V. So that would be like if the V was right here. This would be U. V is right there. I get what they're saying. So the W1 is parallel to V. W2 is orthogonal to V. All right. The W1 is called the projection of U onto V. This is U here, right? On to V. This is V. It's not really clear there, but this is V. The hardest part for me with the projection thing is remembering which one's which here. The projection of U onto V. It's just, I don't have any other way except for you say U first. It's the biggest one. U is the vector that we're going to shine the light on down onto V. The big thing here that we can use is number 2 here, W2 equals U minus W1. So if I know the projection, W1, and that's the X, the horizontal component, it can be a Y component too, it depends how we look at it. And then W1 is the orthogonal. So here's some pictures of this. One, when there's an angle that the angle between is acute, you can see that if I were to put a sun up here and shine the light coming straight down, we would take U and you would get W1, that whole vector all the way across. That's what the shade would be covering up the shadow. W2 is the vector that is orthogonal to the vector being projected on. It is orthogonal to V. W1 is parallel. That's the projection. W2 is the orthogonal, and that is our vertical. You can see how the X and the Y make up the distance going all the way across to U. We can do the same thing here. W2 is orthogonal to V in this picture. It's orthogonal. Makes a right angle, 90-degree angle. W2 is parallel. They go, even though they go in different directions, they are parallel. And the projection of U onto V gets me W1. Now, it's kind of weird because projection onto, like on this one, you're like onto this V, right? But here, the projection is nowhere near V because V is over here. Doesn't matter. So don't let that trip you up. It doesn't have to actually be on top of the vector, just on top of the line for that vector. All right, so this problem is going to go pretty quick. Example 5 here, find the vector component U that is orthogonal to V. Okay, we have V there. They are wanting us to find, we have the picture here, we have U that I plotted, or they have plotted, and we also have V, 4, 3, and they want us to find W1 and W2. All right, well, they gave us W1. W1 is U. I lied. U is here. And we're looking for W2. Did they give us W2? No. Okay, so we need to find a couple things. If I want to find, we don't have a way to find W2. All right, I don't like my wording here. That's what I'm getting confused about. We're going to find W1 and W2. How about that? Okay, so they gave us the projection. The projection here. So if you notice this line, we're working off the picture here. Here's my projection. Right? So they labeled this out. This is 8, 6. That's the point where it reaches. So the vector W1, which is the projection of U onto V, is 8, 6. They also gave me U. And I know that U, so that's 5, 10, is equal to W1, which is 8, 6, plus W2. I know that those will hold. So we could think about a couple of ways. You can think subtraction. You could just think about what do I have to add to those to get W2. W2 is this side, which is my orthogonal side. So we are finding W2, just like the direction said. Forget our little vector arrows. And then I'm just thinking, what do you add to 8 to get a 5? Well, that's got to be a -3. What do I add to 6 to get a 10? That's got to be a 4. So if you look, W2 does go -3 over and 4 up. That is the direction. So the whole point of this problem is to know that if I can find W1 and I have U, I can find W2. Or vice versa. If I have W2 and I have U, I can find W1. And then also, if I gave you vector components of U, W1 and W2, you could add them together to get the actual vector. We're actually not going to do a whole lot of projections in this section example-wise, but we will get there. All right, so with that, we actually need to have some kind of formula. It's easy. If I have W1, I can find W2, which means I would need W1. I need the projection. I'm not going to talk about how this comes about. If you're curious, come ask me, and I can send you some resources about maybe how to derive this thing. I just felt like kind of looking over it, like I'd be wasting a little bit of time. It's quite a bit of work. All right, there's our formula. All right, the projection, and then we're going to read this one last part because it's going to give us a different definition here. So I'm going to put an equal sign here. We can add another definition. If you follow their logic here, what they're doing is they're breaking up V into, so all they did is write down the right side of the equation. They made V now, this part, a unit vector. Notice that is a vector over its magnitude, which is a unit vector. So it's the direction of V. And then it's going to be plus or times this. This is the direction, that's the magnitude almost, like of the actual vector, or answer the projection. That would be what we're multiplying times our direction. So in this case, they just name this K, right? They just called it K. And then they said, okay, K is equal to that thing. If I look at the definition of, so I'll write this out here, cosine of theta equals u dot v, both vectors, divided by the magnitude of u times the magnitude of v. Well, if I look, uv over v is equal, if I times both sides of the orange equation here by the magnitude of u, the left-hand side will look like this, the right-hand side will look like that. So the other definition we could use is I could just replace that, so I get, how do we want to do this? The magnitude of u divided by the magnitude of v, all right, cosine of theta. So this would be like if they gave us an angle instead. Cosine of theta times v. So that's a different formula I could use if I wanted to.